Thank you for the introduction. I'm with the University of Tokyo and SQAI. My name is Okubo. I'd like to talk about the generative models using tensor networks and their embedding into quantum, which we're working on at the SQAI. So I'd like to talk about the U of T efforts related to the SQAI. So we have the endowed chair of quantum software in the Graduate School of Science, and that's where I belong. So we aim to develop new quantum machine learning methods and quantum applications by combining quantum computers with information compression and extraction techniques such as tensor networks and sampling. And we do education around that. So Professor Todo, head of SQAI, and myself, and several other professors working on this. So at the endowed chair, well, we have many sponsors, companies represented here. And in terms of human resource development at our endowment course, these are the things that we're doing. So for research, well, based on the research, we do quantum software symposium twice a year. Next one is June 30th. So please look us up. And soon there'll be some information about the symposium. And also we have lecture at the university and open seminar for general audience. And also we have quantum software hands-on, where U of T students and researchers at companies come together for hands-on. This again is explained on our SQAI website, so please come and look. And so the concept is it's a very small-scale activity. We have limited budget and staff, but the tensor network and sampling are the keywords because that's where we have our strengths. So not just quantum computers, but also we do research about quantum-inspired classical and classical-inspired quantum algorithms. And we have companies involved from quantum device manufacturers to quantum computer users. So people from industry are directly engaged in our activities. And we are recruiting more companies that can support and agree with the purpose of this endowed course. We look forward to you contacting us. So much for advertising. And now let's go into the main part of my talk. Today I'm going to talk about how to use a tensor network for quantum computing. So first, let me explain what is a tensor network. Many of you probably know, but let us recap. So tensor network, you're looking at tensors, and that is expansion of many vectors and matrices. So on the right, so you see graphical representation of tensors network. So tensor is this object with a line, and by connecting that, you can represent contraction. So in Q2B, I think you've seen this diagram many times, so I think you're getting familiar with this. And so you connect many tensors, and you have a tensor network. And so everything is used for research. And so most effective use of the tensor network is to represent quantum many-body state like quantum spin or qubit. And the coefficient is a tensor. And so you have exponential number, and you can use a tensor network to approximate. And you use entanglement structure so that approximation goes well. And so the number of degrees of freedom becomes linear. So amount of resource you need can be reduced. You can represent it in and handle it in classical computer as well. And in quantum state, low energy state, compared with a random state, has only small entanglement that is known. And so by using that as pre-given knowledge, tensor networks can do high precision approximation. So tensor network structure and entanglement relationship I will explain here. Tensor network, as I said, uses entanglement structure to design networks. So if you change the network structure, the property of the entanglement that can be represented will change. And so you have the bond dimension and system length, number of qubits, and then there's the entanglement entropy S. So if you change the network, the entanglement scaling, how does that change is shown here. So on the left, you have a first dimensional or one dimensional, and so no matter how large you make the tensor, then you get a log resolution.
So this can show the long distance entanglement, but in the case of scaling, as in the case of MPS, this is not dependent on L. And then the second from the right, this is very similar to the tree, but there is one, the red graph. So that with this entanglement is a system size 4, so that is log L. And tensor is not the one-dimensional, but if you put that into the two-dimensional path, then in that situation, this is in line with the area, so L to the D minus 1, and this is the area low. And so this tensor network is in line with is similar to the scaling. So in the case of this kind of state, we know that the certain things would happen based on this. So that's the reason why we are able to choose good network. And on the other hand, the tensor network can be used in various areas. So it is possible to view that everything is a tensor. So here, it is not that we are not utilizing the quantum entanglement, but rather this is utilizing the correlation of the information. So this is the image dataset, and this is rather broad, but this is the dataset, say 32 times 32, and then the 7,200 data points. So you have here, so you can see this as a tensor with 4 legs. So this way you are able to have the factoring, and then this way you are able to identify the characteristics of the image dataset. In recent years, we have many applications, neural network. For each layer, you are able to reduce this. So this way you are able to increase the speed of the calculation. And this is not only that, but also this has been already covered by Dr. Todo. But in recent years, we have this kind of differential the equation. So this is for the binary. This is the time evolution based on the Tn representation. So this way we are able to solve the problems of the liquid. So this is sometimes very good the affinity with the quantum computing. So this might be the area for the application for the tensor network. So as can be seen, this is one of the example of the application. Here we have the generation model and with the tensor network, and this is a combination of two things. One is that utilizing the tensor network, we are able to come up with a generative model. And one more thing is to put or embed the contemplar into the quantum circuit. So this is what we are thinking about. This is based on the status of this. So with the ChatGPT, this is not something that is difficult, but rather this is quite easy. So the learning of the probability distribution, it can be studied, and then based on that, automatically this is generated. So that means that the image can be when the image dataset is learned, then this kind of image is generated. Here, this is the 096. This is the handwritten image, and then this is the dataset, and then the probability is calculated, and then for each the image, the n number of pixels can be seen. So that means that n number of 0 or 1, which is white or black. So this is 0 or 1 bit. And so as can be seen in the bottom, so this is the 0 V, and then the 1 sequence can be utilized. So I'm sure all of you are able to see this. And then for 1 qubit, with the qubit, you are able to express 0. So that means that it is possible to have good affinity with the quantum state. And then this is a PV. And if you want to have a certain kind of modeling for that, then in that situation, modeling can be done with the quantum, the state. So this is called the volume machine. So so that means that you are able to use Bolon, the machine. So to be more specific, when you have the probability-based PV, then in that situation, if you have the background of the quantum state, then you are able to have the modeling for that. What we try to do is to come up with the quantum state, which has a high level of affinity. So if you have the quantum state, then if you have the measurement using Z, then that means that you are able to create the generative model. So this is not what we have been doing. So this is the preceding the study result, utilizing the quantum state to understand the probability, and in what way are we able to express the quantum state. And utilizing the Tensor network, it is possible to calculate this with the classical computers. To be more specific, so you are able to calculate this. So this is called the matrix system. So utilizing MPS, you are able to have something on the left-hand side. So I talked about the resolution or solution. So if you are able to see the increase, if you try to have the larger tensors, then you have the negative graph for the cost function. So this might be difficult for you to see, but with this, you are able to have the higher efficiency to have the higher quality. On the other hand, this is the probability distribution of the image. So is it possible, and is it efficient to have the network, the decomposition using this? So this is a handwritten letter, and whether to use MPS or three tensor networks. And then on the right-hand side, you see the differences of the cost function values in this here. It says TDN, and so the two-dimensional tree type, the tensor network is better compared with the MPS, which is the handwritten one. So negative flow Fricht is much smaller than that. So the performance is better in this regard. So this is based on the preceding research. So utilizing this, we conducted other experiments utilizing the tensor network to generate a model. And when the data set is given, what kind of tensor network structure is optimal? This is not given. We are not able to see that beforehand. So when the data set is given, then automatic the elucidation of the structure is needed. So that's a kind of approach that we have. This cannot be done for every tensor network, but in the case of the tree type, the tensor network, it is easier. So we have the given data set, and network can be rearranged, and this way we are able to have the various kinds of trees, and then we are able to come up with the most optimal model, and then this way we can optimize the generative models, and this way we are able to have much better the approximation, but ultimately we are able to have the correlation, the hidden correlations in the data set. To be more specific, for the image data, if you have this kind of approach, then you have the image, and in the center of the pixel, you have the concentration of the information. So this kind of tensor network that reflects this kind of a structure is created. So in the case of S&P 500, you see the time dependent serial data for the price value, the fluctuation. Then you see the different colors. So you are able to have the random tensor networks, and then you are able to come up with the different sectors. So you are able to have the classification for that. And so even if you don't know the correlation structures of the image set, then using the tensor network, you are able to identify some of the hidden relationships. So using the tensor networks, you are able to have the machine learning of the generative model, and you are able to utilize the tensor network, which is quite effective. And one more thing, which is very important.
So if you represent with a quantum circuit, then you can solve this with a quantum computer, the Born machine that uses a quantum state to express probability distribution. Well, you can do sampling, and then you can have variational quantum algorithm and run the Born machine, where variational calculation using parameterized quantum circuits is done. But there is this barren plateau issue in view PA, and so it's difficult to have huge circuits. One way to solve this, what's being proposed, is the if you prepare a good initial state, then you can mitigate the barren plateau. So with a deeper circuit, you can do this kind of partial differential equation calculation. So variational quantum algorithm, if you do that, if you want to do that, if you have a tensor network that's optimized in classical computer, and if you can embed that in the circuit, that will be good, and you can enhance by having a good initial state. And so this shows that embedding into quantum circuits is possible. The detailed algorithm I don't have time to explain, so I just show you what has been achieved. So as I explained, so if you have an optimized tree-type tensor network, or we were able to get that kind of generated model. So the given tree tensor network, just using 2 qubit, and so you give a problem of embedding into that, and we built an algorithm. And Todo and his students worked together with us. So there's still difficulties, but the right-hand side result is what I want you to focus on. So 2 data sets and probability distribution and quantum state was solved for. And bars and stripes on the left. So it's like a black and white stripe. So what's the probability distribution of that existing? And blue is NPS, yellow is tensor network, a tree tensor network. So you approximate first, and then you embed that into the quantum circuit, and then against the precise solution, how much fidelity, the lower the better. And so on the right hand side, the yellow goes down first. So with a tree tensor network, better performance. And on a horizontal layer, it's a layer depth. So with more layers, better performance. So to a given state, by expressing with the tensor network and embedding, so tree tensor networks better in this case. Right hand side, this is more physics. So second order Heisenberg model. So compared with MPS, TTN has higher fidelity to the true state, and so tree tensor network is more advantageous when representing in quantum circuit. So you can do quantum machine learning using tensor network. So to summarize, tensor networks can be applied to various problems. That's what I explained. And so using tensor network, generative model can be constructed. And by structural optimization, tensor networks can find hidden relational structures in dataset. That's what we learned anew. And by embedding tensor networks into quantum circuits, we may improve the performance of the quantum machine learning. That will be all. Thank you very much.